Okay, let's get started. So first of all, Selamat Raya for those menyambut Hari Raya. Basically, there are a few announcements. Satu, the assignment 1 dengan assignment 2. We agreed to postpone the due date for the assignment. Jadi assignment as communicated in the WhatsApp, the due date for the assignment is on the 12th June, 12 midnight. 12 June, 12 midnight. Okay. I look at assignment 1. Assignment 1 tak ramai lagi yang upload the so please upload. I've changed the due date to 12 June midnight. Okay. So any questions on the assignment?
No, sir.
Right. So secondly is our exam. So midterm exam will be on the 10th of June, starting at 5 p.m. Starting at 5 p.m. So it's going to be 2.5 hours. 2.5 hours, 10th of June, 5 p.m. So please make yourself available during that time. Okay. All right. So for today sessions, we're going to take a look at new topics. Basically, this topic is something to do with coating technology. Just to give you example, if you look at, if I'm quite sure you are dealing with cutting tools before. When you look at cutting tools, sometimes the cutting tools for turning machine, for example, cutting tool insert. So the cutting tool sometimes looks, the color is sometimes black, sometimes gold color, sometimes bluish in color. So the various color of the cutting tools is actually due to the coating. So some cutting tools, the substrate materials of the cutting tools itself is carbide, maybe it's tungsten carbide. Sometimes it's a high-speed steel, but it has a different color, and the color is due to coating being applied on the surface of the substrate. So we're going to look into coating technology today on how coating is being synthesized and deposited on the surface of an artifact. Okay? So what we're going to cover today is we're going to look at explanation about coating, what is coating, application of the coating, general coating process, and going to concentrate on the gaseous phase of coating. And in the gaseous phase of coating, there are many types, but we're going to cover two types of coating. One is PVD, stands for physical vapor deposition process. And secondly, we're going to cover CVD, which stands for chemical vapor deposition process. So both of them are a vapor gaseous process, a vapor process. Yeah. So again, if you have any questions, just stop me, and then you can ask me either audio or by chatting. Okay, so why coating? So the application of coating is actually to improve surface properties of an artifact while maintaining its bulk property. So for example, this is cutting tools, and usually cutting tool is made by tungsten carbide or HSS, high-speed steel, so on and so forth. But if you want to change the property of the coating such that it can last longer during machining, then we can deposit a coating materials on top of it. And usually this coating material is much more superior compared to the substrate, the base materials. Right? For example, in this case, is a coated cutting tool. So this is cutting tool insert. So we're going to look at the fractured image of it. So the substrate is tungsten carbide, and the coating is titanium aluminum nitride. So So this is the SEM image of the fractured coated cutting tools. So you can see, so this is basically the substrate itself. So this is made of tungsten carbide, and on top of it, on the surface, you can see a very thin layer of coating. So this is titanium aluminum nitride. So titanium aluminum nitride is much harder, much harder. The hardness is much higher compared to tungsten carbide. So basically, this will protect the tungsten carbide and make it last longer. So the thickness of this tungsten carbide, the thickness of the coating for this for this titanium aluminum nitride coating is about 1 to 2 mils, 1 to 2 microns. So very thin. So our hair is about 100 microns. So you split your hair into 50, then that's the thickness of the coating we're talking about. So that's the purpose of coating. So you want to improve surface property of an artifact while maintaining its property. Right? Applications of coating technology. So where is it being applied? So in many fields. For example, a camshaft. So this is camshaft for a car, or piston for a car, for that matter. You know, so coating is being applied such that it changes the surface property of an artifact of the camshaft or a piston, so it can last longer. Cutting tools, mold die. So if you look at the mold die, so if you work in industry in the molding industry, then you can take a look at the mold die. Sometimes the mold die is even though it's made of steel, but the color is not steel color. Maybe it's black, maybe it's gold color. So basically, the change in color is due to the coating on the surface of that particular artifact. So this is cutting tool. So you can see the gold color cutting tool. So this is a drill bit. The gold color indicates that it's been coated by titanium nitride coating. Titanium nitride. So if titanium nitride coating is going to be gold in color, if titanium aluminum nitride is dark grayish in color, right? If it's a diamond coating, then it's a black in color. And also being used, coating technology also being used in fittings. This is for the visual appearance of a part. So it can also be used, to improve the visual impact of the parts. You can also use coating. Other applications, let's say for example, electronics component, optical, aerospace. For example, if you buy glasses, right? If you buy glasses, cermin mata, then basically usually they will ask you what kind of lens do you want. And then they will start to ask you, do you want to have a scratch free glass? So if you want to have a scratch-free glass, what they do is they're going to put a coating on top of the mirror, on top of the glass itself. So usually that's a particular application. They use a CVD, chemical vapor deposition process for that. Right? So application of coating technology is huge. So anytime you want to change the surface property of an artifact to improve it, and not changing the substrate material property, then you can use coating. This is some examples of the benefits of coating. So if you look at the mold die, so you can see some indications of wear and tear over here. Right? And if you coat it using another coating, titanium aluminum nitride, then you can see there's not much of indications of scratch there. Turning tool insert. So this is a turning insert. So this is the cutting edge, right? So this is the cutting edge. So this is uncoated. So this basically this data I gather from publication, from experimentations by other people. So if you look at the flank wear, So compare this flankware to that flankware. So if you use coating, then basically you're going to improve the performance of that particular cutting tool. This is examples of coating applied on drill tips. So this is the drill tips. So this is the tips of the drills. You can see some wear and tear over here for the uncoated. Compare that to this area of wear and tear of a coated drill. So you can see the difference in terms of performance, right? So, so these are some of the benefits of coating, and coating also can be used as a thermal barrier, so or lubricant of an artifact. So the application of it is actually huge. A general coating process. So if you look at the coating process as a whole, there are many types of coating process. You can categorize it in these 4 categories. One is gaseous phase. The other one is molten phase, solution phase, solid particle phase. So basically, the category reflects how the coating is being deposited, or how coating or a layer of coating is being developed on the surface, right? So gaseous phase indicates that the coating is actually deposited from the gaseous phase of materials to solid phase. So molten phase indicates that the coating material is being molten. So once it's melted, then basically you apply the molten coating materials on the surface of the artifact. And examples of a process is a thermal spray. Thermal spray. So there's a process called thermal spray, where you evaporate the materials and then spray it on the surface. Or coating also can be done using solutions, galvanic or chemical process. So this is basically plating process. So due to galvanic differences, then basically you can coat an artifact, a substrate, with other materials. Or you can do solid particles. Example is like sintering, hard facing. So you can do solid particle coating process. But in this particular class, we're going to cover one particular area of coating, which is gaseous phase coating. And it's gaseous phase coating. Basically, there is a evaporation process, sputtering process, ion plating process, chemical gas phase process. We're going to only cover 3 processes under the gaseous phase coating process, which is sputtering, evaporations, and chemical gas phase. So this is we're going to concentrate on gas phase coating process. So far, any questions?
No, sir.
No, sir.
Okay, there's one question here. Other than titanium aluminum nitride, what is the coating material that's commonly used in industry? So as mentioned just now, so in industry, so if you look at the examples that I showed just now, right? So this camshaft, basically, maybe this is titanium aluminum nitride or diamond coating, because it's grayish in color. So if it's, let's say, for example, if it's goldish in color like this, then basically this is titanium nitride. So you have titanium nitride, titanium chromium nitride, you have a chromium carbon coating, you have many type of coating materials, depends on your applications. So but in the cutting tool industry, what's common is titanium aluminum nitride, titanium nitride, diamond coating, and also basically those two. So you're talking about titanium, aluminum, nitrogen, and also diamond. I hope that answer your questions. Okay. So so as mentioned just now, we get to concentrate on the gaseous phase of coating process, and on the gaseous phase of coating process, there are two different processes. One is called PVD, physical vapor deposition. The other one is called chemical vapor depositions, or CVD. Right? So the basic difference between PVD and CVD is the initial state of the coating materials source. So for physical vapor depositions, right, the initial state of the coating material is solid. I refer that to as a target material. And for CVD, chemical gases referred as precursor gases is the initial is the initial state of the coating materials. So let me just try to explain it a bit. So for example, if let's say for example I want to coat titanium aluminum nitride, right? So the initial state of the coating material before it's being transformed into gaseous phase will be titanium aluminum solid, like a bar, right? And then we have gases inside the chamber. Then basically we convert the solid titanium aluminum target into gaseous phase. It will combine with the nitrogen, and it deposited itself on the substrate and become titanium aluminum nitride. Right? So that's what it meant by the initial state of the coating material source. So for PVD, initial state of the coating material is actually solid. For CVD, so this is chemical. So the initial state of the coating material is actually in chemical form. In chemical form. So again, we're going to cover both physical vapor deposition and also chemical vapor depositions. But we're going to cover for the physical vapor deposition, we're going to look into sputtering and evaporation. Sputtering and evaporations only. So let's look at the PVD coating process, physical vapor deposition coating process. So this is basically the setup of the equipment for the PVD equipment. So what we do is basically the items that we want to coat. For example, in this case, this is a drill. This is a drill bits, right? So we put the drill bits on here, and we call this we call it the what do you call it, substrate table. We call it substrate table. So we put whatever we want to coat over at the center, right? And over here we have a arc or magnetron cathode. So we have a cathode over here, and this is where we put the target material. So let's say for example, if I want to coat this drill, and the coating is going to be titanium aluminum nitride, then this particular target will be made of titanium aluminum alloy. Titanium aluminum alloy. So basically, what we do is we attach the target to the magnetron here, arc or magnetron system here, and we put a power supply and we bias it to be negative bias. Okay, so this is where you put your substrate to be coated. The coating materials in the solid form is attached here and is negatively biased, right? And the substrate also usually is negatively biased. Okay? And usually we have these three-fold rotations on the substrate. So basically this table will rotate. The table that's holding this drill will also rotate. So the rotation is to make sure that even coating can be applied, as much as possible. Even coating can be applied on the substrate. So if you need a process, so over here you put the process gas in here. So the process gas usually is going to be inert gas, for example argon, and basically the whole process need to be done in vacuum. So you have a vacuum pump to pull the vacuum from the system, and there's a heater at the back to heat up the substrate during the process itself. Yeah? So basically, those are the basic setup of a PVD. So you have a substrate sitting on the substrate table, which is rotating. The target materials is at the sides, usually depend on the side on the bottom. Then is negatively biased. So process gas enter the system, and the substrate holder is also is going to be biased. And you pull a vacuum so that you create a vacuum inside the chamber. Okay. Okay. So during PVD process, there are two process actually that I want to explain. One is, so this is a target. As I mentioned just now, since this is a physical vapor deposition, the target is a solid. It's physical. It's a solid target. Right? So that solid target will be converted into vapor. Right? And that vapor will be transported to the substrate and deposited onto the substrate and become a coating. Right? So there are two processes that need to be controlled and understand. One is vaporizations of the target materials, how you vaporize from solid to vapor. Second, how do you transport the particles, the vapor? So when you vaporize the target materials, then it'll become in a form of atoms or ions, right? So how do you transport these particles, either atoms or ions, onto the substrate? Okay? And the difference between sputtering and arc evaporation is in the methods to vaporize target material. So as mentioned just now, in PVD process, we're going to cover two. One is sputtering, the other one is evaporation. So the difference between sputtering and arc evaporation is on how we vaporize the materials. Right? Transportation of particles to the ions the same for both sputtering and arc evaporation. But how the materials is being, the target material, solid target material is transformed from solid to vapor is different between sputtering and arc evaporation. Okay? Okay, so let's look at the basic PVD process. The first thing is you need to have a vacuum environment. So when you deal with PVD, physical vapor deposition process, the most important thing is you want to have a vacuum environment. This will determine reproducibility, uniformity, film quality, process stability. Okay, so questions, is the paint on the car body considered as coating, or is there any, or is there another layer of coating on top of the paint? So basically, this is considered, painting is also considered coating materials. So the question here is there another layer of coating on top of the paint? So I'm not familiar with the painting of the car body. So I assume there must be a premier. It's like a primer, a prime coating that's being placed on top of the car body. But is painting examples of coating? Yes, is example of coating. But we're not going to cover it here. We're going to cover both on the gaseous coating process only, which is more advanced and more complicated. Okay. First we need to have a vacuum environment inside the chamber. So inside the chamber here, inside this chamber, it must be vacuum. It cannot be. The reason why it need to be vacuum, because you need to develop a coating that's reproducible, uniform, the quality of the coating processabilities. But because you have to understand, during PVD process, the solid is being transformed into vapor phase. So basically, from solid, it will atomize. And in the vapor phase, basically the materials exist in terms of ions and atoms. So if you don't have a vacuum inside the chamber, then you have other elements. Then you have oxygen, you have carbon, you have many other elements. Then basically you're not going to get a good quality of coating. Let's say, for example, if you want to produce titanium aluminum nitride, if you don't have a vacuum chamber, you have oxygen inside there, you have a carbon inside there, you have other gases inside there that will change the compositions of the coating. That's why you need to have a vacuum inside the coating chamber. And basically the requirement is between 10 to the minus 5 to 10 to the minus 7 millibar. That's very low, very low pressure inside the chamber. So basically, usually when you pull the vacuum system from such PVD system, you have to do two stage. One is with a pump, and then you have to use a turbomolecular pump actually to pump out all the elements inside the chamber to all the atoms inside the chamber to the outside environment. So you have to achieve about 10 to minus 5, between 10 to minus 5 to 10 to minus 7 millibar. So before you do anything in the process, you have to vacuum it first. So two main purpose to achieve this condition before initiating of sputtering process are: one is contamination minimizations, as I mentioned just now. So inside the air, there are many things. Gas, there are other gases, oxygen, so on and so forth, and there are also particles, and there are also carbon flying around, right? So basically, we want to pull the vacuum from the chamber because we want to minimize the contaminations. The other reason why we want to create a vacuum inside chamber is basically maximizations of particle mean free path. So if you learn about gas inside the movement of the gas, then you know what is mean free path. So this is mean free path of a particle is the average distance covered by a particle, either photons, atoms, molecules, ions, between subsequent impact. Means that, so from here, let's say, for example, this particular atoms moves, right? So this particular atom moves. So before it hit another atoms, what's the distance? So when it hit these atoms, then it will move to this and collide these atoms, so on and so forth. So the mean, the average of the distance traveled by a particles, whether it's atoms or ions, so on and so forth, is basically the mean free path. And we want this to be as long as possible. We want the mean free path to be as high as possible. And I'm going to explain to you why before collisions. So this is the what do you call it, the graph on the y-axis over here. You can look at the mean free path. On the bottom side is the pressure. So if you look at it, the lower the pressure, right? The lower the pressure, the higher the mean free path. So if you look at the mean free path, this is 1, this 10 to the power of 2, 10 to the power of 4. So as it goes down, it increases in value, right? So so this is pressure. So this is low pressure, this is high pressure. So the lower the pressure, the higher the mean free path going to be. For example, if you have, let's say, for example, 10 to the minus 6 torr, it's going to be 10 to the power of 6 millimeter in terms of mean free path. But if the pressure is 10 to the minus 1 over here, then it's only 10 millimeters. So basically the reason why we want to make sure that the mean free path is as long as possible, because just imagine if if this guy, this is, let's say, for example, an atoms want to travel to here, and this is for example a substrate, right? So as it moves towards here, if there are too many gases inside here, so if you have higher pressure, it means that you have many gases molecules inside it. So it moves, try to reach the substrate surface, then it will collide with other atoms. So basically the energy of it will not be high enough, and also it will not be able to deposit itself on the surface because it's being deflected by other atoms. So if there is no no such atoms in here, molecules in here, then this particular particles can just move directly and deposit itself on this particular substrate. So that's why we want to make sure that the mean free path is as high as possible in the PVD process. Okay, so again, the purpose of the vacuum is the two main purpose. One is contamination minimizations. The other one is maximizations of the particle mean free path. Okay, so let's look at the vaporizations. So so we're going to cover vaporizations from solid to gaseous phase for two processes. One is magnetron sputtering process. The other one is arc evaporation process. Okay? So this is overview of a magnetron sputtering process. So during sputtering, energized plasma ions strike a target, which is composed of desired coating materials, and thus atoms from the target to be ejected with energy, high enough energy to travel to and bond with the substrate. So if you look at this illustration, so this is substrate area to be coated. Yeah? This is target. This is target materials. So this guy, if you see this red color semicircle, is indication of magnetic field. So this is magnetic field. So over here we have magnets. So you have magnetic field in here. So the purpose of these magnetic fields is basically magnetic fields will trap electrons. Magnetic field will trap electrons. That's why if you want to if you heard news saying that Pemancar Telecom, the telecom what do you call it, the antenna, right? Some people don't like disagreed for that particular antenna to be built close to the housing area, because the antenna actually will have some field, some magnetic field, and some wave, sort of like wave, and that thing will actually trap electrons. And when you have a trapped electron in as such in here, the electron will move along this magnetic field, and the electron moves at a very, very high rate, very, very high speed. So as it moves along this particular magnetic field, then basically it will collide with the process gas in here. And the process gas, as I mentioned just now, usually is an inert gas, and usually is argon. Right? So when these particular electrons that move along the magnetic field collided with argon, so argon will lose electrons, and it will transform itself into what you call it, into ions. So now, rather than argon atoms or argon molecules or argon gas, we have argon what do you call it, ions. And these argon ions is positive in charge, right? It's a positive ions. So as I mentioned just now, the argon ions is positive, and as I mentioned just now, the substrate is negatively biased. So if you remember in this, yeah. So the target is negatively biased. The substrate is also negatively biased. So what you have is on the surface of this particular target materials, you have this magnetic field. And because of the electrons moving around that magnetic field, it will collide with a process gas that's pumped into the system, which is argon. So argon now converted into ions. Right? So once you have these argon ions, then basically these argon ions will be attracted to the negatively charged uh, target. So you have accelerations of the argon ions onto the onto the target surface. Okay? So for example, on this particular case, this particular argon ions accelerated towards the surface of the target. So once it hit the target materials, it will eject an atoms out from target. So this is the conversion from solid to gaseous phase. Okay? So during sputtering, energized plasma ions, energized plasma ion, which is argon ions, strike the target, which is composed of the desired coating. So target is made of the desired coating material. Cause atoms from the target. So atoms from targets ejected with enough energy to travel to and bond to the substrate. So just imagine if this is not a vacuum, then this atom, as it moves towards the towards the substrate, it will collide with other atoms. Right? You don't want that. So that's why you want the mean free path is to be high, such that these atoms can travel and move and deposit itself onto the substrate. Okay. Vaporizations of the target materials, magnetron sputtering. So in magnetron sputtering, the process